here and then move maybe to the next next speaker. I don't know who is chairing the next session. Anne?
I'm chairing the next session. Peter. I'm Peter. I'm chairing the next.
Okay, go ahead. Yes, Peter. I see you. So go ahead, Peter, and then we move.
So first of all, I'm really amazed at all of the very enthusiastic and active participants. So it's very great. So the next session, we first have an invited talk by Stuart Russell. So let me introduce Stuart Russell. He's professor of computer science at UC Berkeley. And in fact, I was a student there, and I think I left just when he arrived. So I saw him as a young professor there. Stuart Russell has, he's has many awards. He's holder of the Smith Sada Chair in Engineering, director of the Center for Human Compatible AI. He has the IJCAI Computers and Thought Award. He held the chair Blaise Pascal in Paris, and he has a number of awards, fellow of the AAAI, ACM, and AAAS. And there's, of course, everybody knows the book Artificial Intelligence, The Modern Approach, written with Peter Norvig, and in several editions. It's a really excellent text, standard text in AI. So it really has a very broad and deep knowledge. So I would like to now present Stuart's invited talk, which is called Logic, Probability, Knowledge, and Learning. So, Stuart, you're there, I think. I saw you.
Yeah, I am. Thank you very much, Peter. So if I remember correctly, I might have been on Peter's qualifying exam committee.
Yeah, I remember.
Presentation committee. I think he's forgetting that. So we overlapped by maybe 4 years, I think, altogether. Okay, so let me share my screen.
Share your screen.
And we will get going. Okay, good. So I put a lot of words in the title because I wasn't sure what I was going to talk about. So that gave me some freedom. You know, I in some sense I want to start from the present. So in the present in AI, people are looking at things like like the victory of AlphaGo over Lee Sedol, the ImageNet, visual object classifiers, and many other successes of deep learning. And they are wondering, okay, maybe logic is a waste of time, all that old-fashioned AI stuff. The vast majority of students are not interested in it. And the vast majority of papers published now in AI conferences don't have a single reference before 2012. Deep learning people are saying things like, you know, perhaps one day we could aim for, you know, the capacity for our systems to actually know things and reason, you know, as if no one has ever thought of that before, and this is still far off in the future. So there's a real conceptual chasm, I think, between the modern AI machine learning community. And we are going to have a panel on this subject later on. And to me, the reason why, so just let me turn off my phone. The reason why this is not going to work in the long run, just applying deep learning, is this issue of expressive power. So if you're trying to learn using feed-forward circuits as your fundamental knowledge representation, you know, we don't think that if we were going to build a payroll system for IBM, you know, we would write it using feed-forward circuits. People haven't used feed-forward circuits to build computing devices since before the Second World War. And the problem is that they have necessarily very large function representations that don't actually capture the regularities of the universe. And so as a result, you get very little generalization and very, very slow learning. So, you know, if you compare what happens with the ImageNet visual object recognizers, they might need 100,000 photographs of giraffes until they are competent at recognizing giraffes in a wide variety of circumstances. You can't buy a children's picture book with 100,000 pictures of giraffes. They only have one, or maybe there are 2 giraffes in one picture. And that's it. Why? Because humans learn from very few examples and they generalize extremely fast because they've captured lots and lots of abstract regularities in the universe already. So we'll just take the rules of chess as an example, right? If you try to write those down using finite automata, it's going to be about 10 to the 38 pages. Because you're talking about transitions between completely specified board states. And that just is going to be, and that would be true for hidden Markov models, any kind of system that has a transition matrix between states. If you try propositional logic, it's a lot, maybe 100,000 pages. You have to repeat the definition of every move, the definition of checkmate for every square, for every possible time step during the game, et cetera, et cetera. And this will be true for all sort of the circuit languages, including neural networks, Bayesian networks, other graphical models. These are factored. They go a little bit beyond the atomic states of automata theory, but they are just bit vectors or analogous representations. So the atomic elements of the representation for chess would be something like the white king is on c4 at move 12, right? That will be an uninterpreted symbol for a circuit language. And of course, that writing the rules of chess using those kinds of uninterpreted symbols would be very hard. So first order logic and programming languages and various other formalisms, they separate out, for example, the predicate and the objects and allow you to quantify over the object. So you can say, for every square xy, for every time step, for every color, for every piece type, there'll be a piece of that color on that square at such and such a time, if and only if, and then you can basically say, it was there before and it didn't move, or there was nothing there before and something moved onto the square. And you can write the whole rules of chess in a page of first order logic. I'm not sure, Patrick seemed to suggest that it's really, really hard to write anything in first order logic. Maybe we could talk about that later. And I'm not particularly wedded to first order logic. It just means languages with roughly this kind of expressive power. So this drawback of very slow learning is not going to be limited to just feed-forward circuits, but actually any language where the runtime execution of the learned model is linear in the size of the model. Because that means that to learn distinctions in superlinear languages is going to require superlinear representation size. And so to learn distinctions that are NP hard is going to require probably exponentially sized circuits. And so there's no trade-off allowable between sample complexity and runtime complexity. Whereas with an expressive language, yeah, you're going to pay in runtime complexity, but you can gain in sample complexity. In the real world, that's what matters. Okay, so having started from the present, now let me go back and talk about a sort of a very skewed history of AI. So when we started building AI, we said that the first thing to do is, can we describe any kind of algorithm that achieves any kind of intelligent behavior? And what we might call bad old-fashioned AI mostly ignored computational tractability. So they said, look, we've got an algorithm that comes up with this 4-step plan. Or we've got an algorithm that can tell the difference between an A and a B in an image. And they said, oh, from there, it's just, it's easy, right? It's just a matter of making, scaling up and we'll be done. And that's because this was really before we even knew about computational intractability. And I think deep learning is making the same mistake, except with sample intractability. So the assumption that we can just solve the problem by making the circuits and the data sets bigger and bigger and bigger and bigger is ignoring the fact that the universe simply can't supply nearly enough data to train circuits to do things that require more expressive languages to capture the regularities you want. And some people in deep learning are starting to realize this. So here's Francois Chollet, who's author of one of the big deep learning packages and a very good deep learning textbook. And this is from the last chapter of his book. He says, many applications are completely out of reach for current deep learning techniques, even given vast amounts of human annotated data. And the main directions in which I see promise are models closer to general purpose computer programs. So as I mentioned before, he's looking to a future in which people are learning something that's as expressive as general purpose computer programs, perhaps not realizing that that's actually been going on now for donkey's years. And parabalistic programming, for example, the first papers came out in 1997. So if you go back again to the beginning of AI, we wanted to have intelligent systems in the real world. And if you look at your desk, you will see a lot of objects on your desk. Maybe you even have a chessboard on your desk. So you say, okay, the world has lots of things in it. Pens, chess pieces, bits of paper, cups. There's a microphone on my desk and various other things. And so if you talk about a world that has things in it, you need a mathematical formalism where things are there. And first order logic is one such. And I think this is the main reason why good old fashioned AI chose first order logic as its core representation. But if you look out the window, then you might see something else about the world, that the world is uncertain. There's a lot of stuff that's hard to predict. Your percepts don't give you full and perfect information. And so you have to capture uncertainty and manage that. And we in AI sort of took this seriously in the 80s. Obviously, other areas like dynamic programming had taken this seriously for a lot longer. And so we produced things like Bayesian Networks as a formal representation for uncertain knowledge. But of course, this is a circuit language. And so we very quickly ran into restrictions of expressive power that prevented us from writing Bayesnets to capture complicated problems. So what do you expect happen? Well, of course, the first order logic people, even John McCarthy, recognize that there is real uncertainty in the world, and the Bayesnet people recognize that the world has things in it. So you get some kind of unification, of first order parabalistic language, something that uses the syntactic machinery of logic to gain that expressive power to capture complex regularities in worlds with lots of objects, plus the machinery of probability theory to handle uncertainty, to learn from additional observations using Bayesian updating, et cetera, et cetera. But there's one other thing that's really important that happens when you combine these two observations, that the world is uncertain and has things in it, which is that you don't know what things it has in it. And this is really important. And it wasn't actually for quite a few years after the early first order probabilistic languages were developed that people noticed that they still had expressive limitations. They required you to know exactly all the things that existed. And that doesn't really work in the real world. You know, before you open your eyes, you don't know the objects that you're going to see. Before you open a book, you don't know the characters that are going to be described in the book. So you have to allow for uncertainty about what exists. And then parabalistic reasoning is going to lead you to believe that some things probably exist and are probably the same or different from other things that probably exist. So we call this open universe parabalistic languages. So open universe meaning that you don't have a closed universe assumption that you begin with. So let me just try to illustrate this very concretely so that, that everyone is on exactly the same page about this distinction. So if you have a language with two constant symbols A and B and one relation symbol, so that's it. Okay, so that seems pretty simple. Now in the closed universe semantics, which sometimes called Herbrand semantics, or what happens in logic programming, if you have two symbols, then they're assumed to be exactly two objects that they refer to. So A and B are assumed to be different, and because it's closed, there are no other objects in the universe. So all the possible worlds have exactly two objects. And the only thing that you're not sure about is how those two objects are related to each other. So that it turns out that there are exactly 16 possible worlds, and they all look pretty similar, and it's relatively easy to put a probability measure over those. With open universe semantics, which is what real first order logic as opposed to logic programming has, then A and B could be the same, or they could be different, and they could be objects other than A and B in the possible worlds. And so here I just sort of enumerated some of the possible worlds up to sort of a middle-sized one, but obviously they go on forever, and there's infinitely many possible worlds, and they all look, you know, they look arbitrarily different from each other. And so the trick is, how are we going to put a probability measure over all of those worlds in order to do what we already know how to do with Bayes nets, which is to write probability models, to update them with data, to make predictions, to learn, and all the other great things that we would like to be able to do. Okay, so so we developed this language called BLOG, which stands for Bayesian logic. We thought that was a very cute acronym. It's actually completely useless, because if you type BLOG into Google, you don't find our language at all. You find millions of other pages instead. So it's a really stupid idea. But anyway, I'm going to very briefly go over the sort of syntax and semantics of BLOG. And you can think of the statements in the language as, you know, if you want to think of them this way, you can think of them as ways of constructing possible worlds. In other words, you could sample using these statements in order to construct a world incrementally. The first kind of statement we call a dependency statement. And so this says, for some functional relation applied to some arguments, what's the probability that that function or relation has value or is true for its arguments. So just to illustrate that, right? So H is a variable that ranges over houses, so it's a logical variable. So this says, for any house, the probability that the burglar alarm sounds in that house depends probabilistically, according to some conditional probability table, on whether or not there's a burglary in the house and whether or not there's an earthquake in the region of the house. Okay, so here region is a regular logical function symbol. Earthquake and burglary are both regular Boolean predicates, and so on. So we're using the machinery, the syntactic machinery of logic, to write probabilistic dependency statements. And then you would specify this conditional distribution for how the probability of the alarm sounding depends on the truth of these parent variables. So the other kind of statement you need is the statement that actually adds some objects to the world. So for example, because this dependency statement talks about houses and regions, we're going to have some houses and regions in the world. And so we might say the number of geological fault regions is uniform between 1 and 10, and the number of houses in a given region R is maybe Poisson with mean 50. And that's not a particularly good distribution over the number of houses, but just there for illustration. So one important thing here is that the existence of each house is in some way keyed to the existence of regions. So we call the region that the house belongs to as its origin function. Okay, and that will come in handy when we get to the semantics. Okay, so that's basically the syntax of the language, and The semantics starts with what are the objects that occupy the possible worlds. And so in first order logic, you just call them, you can just enumerate them as index tokens, object 1, object 2, object 3. In this language, they have a bit more structure. So first of all, it's typed, but the objects also have their origin. So geological fault regions, if we go back here, right, they don't depend on any other object. Their existence, they just sort of pop into existence by themselves. So they don't have an origin. So an object would look like this is geological fault region number 3 with no origin. But the houses depend on some geological fault region that they belong to. So this is house number 97, whose region is geological fault region number 3. Okay, so every object on the semantic side, in the model structures, every object is one of these typed, numbered objects with its origin, which is some other object that is already in the universe. And then you can to then say what is the probability model being defined here. You define the basic random variables, and then we'll put the probability measure over Cartesian products of all those basic random variables. So each basic random variable is a predicate or a function applied, indexed by one of the objects, and then applied to the possible world. So this would say, this is the random variable. Is there an earthquake in geological fault region number 3? And in any possible world, omega, that would be true or false. Okay. So those are the basic random variables. And then a possible world sets a value for every one of the basic random variables and all the number variables, which say how many of each kind of object, depending on its origin function, exist in that world. And then to make a probability measure, we have to say what's the probability of each possible world. So here I'm only dealing with countable stuff. It's the product of the conditional probabilities specified in the model. Okay, so let me expand on that a little bit, right? So I said it's the probability of the conditional probabilities specified in the model. So for that world to be the case, you had to have generated that number of regions and that number of houses in each of the regions, and then put earthquakes in some of the regions and burglaries in some of the houses and alarms sounding in some of the houses, and each of those things being an event occurring conditioned on its parents. So we would get the conditional probability from the model to give you that product. And this works because for any possible world, there's only one sequence of assignments of random variables that could bring that world into existence. Okay, and that's because each object has its generation history. And if we just use sort of numbered objects without their generation history, then there would be many, many ways that that world could come into existence, and therefore the probability we would assign to it would be some ungodly complicated thing to work out and write down. And it would make the semantics extremely complicated. It would make it very hard to write inference algorithms that we were sure were correct. So this seems to be a little trick that makes this very straightforward. This work was mainly the PhD thesis of my student, Brian Milch, and in his thesis, there's about 100 pages proving this theorem that I'm going to state very, very, very approximately, that every well-formed log model specifies a proper probability distribution over all the possible worlds, i.e. all the first order model structures with the modification that they have these origin functions that are definable given the vocabulary or the signature of the model. So well-formed requires some restrictions so that we don't get cyclic probabilistic dependencies, and we're not asking too much of the language. So I'm not going to go into the details of that. And we have more recently developed measure theoretic extensions so we can handle combinations of discrete and real valued variables where some worlds have different numbers of real valued variables from other worlds, and that can get complicated measure theoretically, but that can all be handled. So here's just to illustrate. So here's a model written in this language. This is called the net visa model, and it's the monitoring system for the Comprehensive Nuclear Test Ban Treaty. So there it is. This took about 15 minutes, half an hour to write, and then took about 3 months to get it to run fast enough to do real-time monitoring for the whole planet. And it's now it is the monitoring system for the Nuclear Test Ban Treaty. So I'm not going to go into great detail, and I'm not. Can people see my cursor as it moves around or not? I'm not sure.
Can see.
Yes. Good. Okay. So just to illustrate, right? So what are the objects here? So there are seismic events that take place, and then so we have to say, roughly how often do we expect seismic events to take place, and then there are detections of seismic events at seismic stations that are scattered all around the world. There are two kinds of detections here. So there are detections that are not caused by events. So these are false alarms, which happen at according to some Poisson process. And then there are detections that are caused by an event. And the number of detections is either going to be 0 or 1 from a given event at a given station. And that's going to depend, according to this is detected predicate, on basically how big is the event, the magnitude of the event, the depth of the event, and the distance between the event and the seismic station. Okay, so I don't want to go into too much detail here because this is getting into geophysics, but a geophysicist can look at this and read it and understand it completely. And they would say, great, so you've written down our understanding of basic seismology, super, but where's the algorithm, right? I mean, so they think of what you have to do as you learn a bunch of geophysics and then you write a bunch of C++ code that takes the data and does something with the data, right? And when I say to them, okay, well, no, we're done here, right? We just apply, in principle, we just apply general purpose inference, so off the shelf, Metropolis Hastings MCMC, and then we have a monitoring system. There is no code per se. Right? Now that's not strictly true because it takes, we have to do more to get it to run fast enough, but in principle, that's true. And that takes a lot of getting used to for a seismologist, given that roughly half the budget for seismology research in the world has gone into this specific problem of monitoring for the Nuclear Test Ban Treaty. They get a bit upset when you say, oh, sorry, this took 15 minutes and we're done. And this works about 3 times more accurately than the previous state-of-the-art seismic monitoring system. Okay, good, okay. And here's just an illustration. This was 2013 when it was running already in Vienna, and the North Koreans set off a nuclear bomb, and instantaneously the net visa algorithm detected it and estimated this as the location. And later we found on satellite images the tunnel, the entrance to the underground testing facility, about 700 meters away from our estimated location. The combined brains of all the best geophysicists in the world estimated the location over here about 2.5 kilometers away. And the blue lines here give the probability contours for where we thought the epicenter of the explosion was. Okay, so briefly I'll mention inference. And as I said, we can do things like Metropolis Hastings MCMC, you can do rejection sampling, importance sampling. And under the usual ergodicity assumptions, these algorithms converge to give you correct answers for any well-formed model, for any finitely evaluable first-order query. So it's no good asking is Fermat's last theorem true? That's not allowed. Probably won't work very well. But any query that can be evaluated in finite time on a possible world, the algorithm will give you eventually a good approximation to the answer. And these are pretty stupid algorithms, right? They don't work. They don't do any lifting. They work much as the earliest Davis-Putnam theorem provers used to work before Robinson's paper, by constructing partial grounded worlds. They're partial worlds because they only contain the values of variables that need to be instantiated in order to answer the query with respect to the evidence. So they're sort of minimal in that sense. And for some cases, they actually work pretty efficiently. I might show you an example later. So this general area, and I should mention that there are really two branches. So I've shown you the declarative branch of parabalistic programming, and the other branch, instead of using first-order logic as the fundamental semantic model, uses the execution traces of arbitrary programs in any programming language. So the possible worlds for this other branch are execution traces of programs. But this area now is growing pretty fast. This shows that we're up to about 2,000 papers a year by 2019. So for those of you who are despairing of modern AI and modern machine learning, just be patient for a little longer, and maybe the pendulum will swing towards something that's more based on expressive representations. So, so I would say, why isn't everyone using this, and why are the newspapers still talking about deep learning? I would say so far the engineering effort is pretty weak. There are few groups, with the exception of Microsoft, I would say, which has a pretty substantial group doing this. So the Infer.net is a parabalistic programming language, and they have quite a few real systems that are running. And so we need to do a lot more work on robust tools and demonstrating a much wider range of applications. There isn't really, for example, a good course syllabus with course materials that is easy for someone to teach if they want to adopt this approach. There is a massive payoff when you do the engineering well. So just as the other David Warren did the Prolog compiler and obtained typically, in my experience, 200 or 300 times faster execution for the same Prolog program. And Peter did a lot of work on this as part of his thesis and showed speeds equivalent to C++, and that's all great. So we can get the same thing here, except what you're doing is you're taking the inference algorithm and the model, the probability model that you write in the blog language, and you're deriving from that a model-specific inference algorithm. So all of the static structure of the model is compiled away. What we've shown is, in fact, that when you're running MCMC, most of the CPU time in the compiled code is inside the random number generator. So the total overhead of doing inference in this very expressive language is almost zero. We compared it with Bugs, which is the most widely used BayesNet package. BayesNet's being, a circuit language, and it's about 1,000 times more efficient than Bugs. And this just shows that you can do computer vision in real time. So on the left, this is tracking moving objects in the OpenCV, which is a handwritten C++ code for tracking moving objects. On the right, this is about a 5-line blog model. And then we run it through the compiler and we feed in video data in real time. And the algorithm is, let me do that again. Right, so the algorithm is able to track the moving objects in real time, running MCMC inference on the model. So the other big thing that we don't do is a lot of what you might call structural learning. So parametric learning within these models is easy. You just put prior probabilities over the parameters rather than specifying their values, and then inference, as you collect data, the inference process infers values for the parameters. So you can do pretty much everything that statisticians typically do can be done very straightforwardly in 2, 3, 4 line blog programs. But structural learning, so discovering new functions, new predicates, in the same way that the inductive logic programming people have been working on for a few decades, that's still only been done in very, very few cases. So I suspect that this will be the next area, and probably an area where we can perhaps borrow whatever it is that makes deep learning able to discover features in its hidden layers, which is essentially stochastic search over circuit structures with massively parallel computation. I think we can try to get that to work in learning the structures of probabilistic programs. Okay, so stepping back a little bit, what I'm basically arguing, and what I think that good old-fashioned AI was based on, is the idea that if you're going to build an intelligent system, it needs to know something. And the alternative is, has to be taken seriously. And so there are people who seriously believe that you can simply learn a direct policy representation, meaning a mapping from percepts or percept sequences to actions. You can just learn that directly as a giant circuit. You don't need to know anything at all. You don't need to have any form of explicit reasoning. There's no knowledge base. There's just a mapping from percept sequences to actions. I would say for the first 70 years of AI, that was essentially just a religious belief, right? Partly based on introspection, partly based on the philosophical traditions, which have tried to understand human reasoning and human capabilities in terms of knowledge, the philosophy of science, et cetera, et cetera. It just seemed kind of obvious that that's how it would have to work. But that belief has been challenged. And for example, in robotics, many successful robotic systems do work by direct policy representations that turn out to be easier to write down than to axiomatize, the physics of the robot and the physics of the world and do a bunch of reasoning and all that. Anyway, so what we mean by knowledge systems, they're going to be modular. So you can sort of look at separate pieces of the system and say, what does it mean according to some semantics based on truth? And they get multi-purpose, meaning you can take that piece of knowledge and use it for lots of different things. And the question is, why do we believe this? What actually makes it true? And it's sort of embarrassing, actually, that nobody has answered or even really asked that question. Why do we think that intelligent systems need to know things and reason? So you could give a kind of a devil's advocate argument, right? So you can go talk to the deep learning people and say, okay, deep learning people, could your deep learning system design a gravity wave detector, right? And they would scratch their heads and say, well, do we have a big database of gravity wave detectors that I can train on? And of course, no, because they haven't been invented yet, right? So naturally speaking, we think of a gravity wave detector as being produced because we know physics, right? Because thousands of people learned things about physics and wrote them down as explicit knowledge representations, and we learned those and took the next step. Another question you can ask deep learning people is, okay, suppose you have more than one deep learning system in the world. Can one deep learning system convey any knowledge to the other, or convey something to the other than simply like dumping all its data right? Is there any way of sharing among systems other than dumping data into a larger database, right? So that's an interesting question that you could ask deep learning people. And I suspect that what we're going to end up showing is that the deep learning view of learning is really mistaken, right? The deep learning view is that data produces knowledge, right? But I don't think that's correct. I think knowledge plus data produces more knowledge, right? And this is how we're able to do gravity wave detectors, because we know a lot of physics already. And then that one ping comes in from the detector, and now we've learned something about what happens with those black holes circling each other on the other side of the universe. And so recently, just in the last 18 months or so, people have started to ask why and come up with some answers. And this comes back to the point I made earlier, that under some assumptions, you can show that there are exponential gaps in sample complexity between model-free and model-based reinforcement learning. So that means that if you have a world where the transition physics is simple, but the policy or the value function can be very, very complicated, because the policy or the value function represents the infinite iteration of the transition model into the future. And so it can be extremely complex. If you try to represent it using, for example, a constant depth circuit, you're going to get an enormous circuit. And that circuit is going to require exponentially many samples to learn it. So I think we certainly really haven't nailed this problem yet, but I think as we make progress on it, we're going to finally get to a fundamental theorem of AI. And that's basically going to explain why you want to build systems that know things. And then we can start sort of building up from that basic idea. Okay, so to summarize, we need expressive modular capability for acquiring and using knowledge. And deep learning doesn't provide that because circuit languages can't capture the regularities of the universe. What I've been pursuing, and others, this idea that you can combine probability theory with first order logic or with programming languages, depending on your taste, or possibly set theory. And this may give us a way forward that avoids the brittleness of the old-fashioned logic-based AI systems.
Stuart, we're going to have to...
we're wrapping up. This is the last one. Yep, so yeah. I'm done.
Okay, very good. Let's say, so I'm eating into a little bit the break time here, but I think that's okay. I think we have time for one or two questions now. There will be a panel on this later, so people who have more questions can wait then. I don't know if anybody has a question. I can ask a question. I have a couple of questions. So how would you say that in this approach, where of course it's building on logic, and the deep learning approach, the uniform framework that somehow combines the two in a comprehensive and a nice way, how does that look? I mean, where it has these deep neural nets, it has all these generative adversarial systems, it does reinforcement learning, and somehow it's also doing your stuff. What is like the principle of that?
Okay, so some parts we can already do. So reinforcement learning is totally neutral about what the representation is, and you can do reinforcement learning with relational representations, first order representations. And we have an extension of the blog language to incorporate actions and rewards. And that brings with it its own set of interesting complications and philosophical puzzles. So it depends on how you think about deep learning fitting in. So if you think about deep learning as being a representationally restrictive but flexible function approximator.
But it's more than that, huh? There's lots of philosophy and lots of techniques that are very clever, and it's more than just function approximation, huh? I mean, there's these generative adversarial things where you have the the parts of the system are kind of fighting each other. And so it's more, there's actually some control in there already, yeah? It's not just a function, huh?
But what, I mean, that's an algorithm for producing, for producing a generative function.
That's considered part of the deep learning, and that increases a lot the power. So there is some synergy between these control and function approximation. I don't know, but maybe we should leave it for the...
Yeah, I
also have more questions. Maybe we should then, if it's okay with Stuart.
Sorry, but Stuart, you'll be in the panel, I guess, so we could do that. Let's go now. So let's thank Stuart for an excellent talk. So I'll give him some virtual applause.